Radioactive decay examples. This is part of the particle waves nuclear reactions. Key areas. Nuclear equations to describe radioactive decay, fission and fusion reactions with reference to mass and energy equivalence, including calculations, coolant and containment issues in nuclear fusion reactions. What we will do today. Go over examples of nuclear reactions in symbol form, carry out problems on the above, find out about Einstein's famous equation E is equal to mc squared, and describe how we use the equation above in nuclear energy and discuss some of the safety issues in nuclear reactors. Example 1. Identify the particle emitted at each stage in the decay series shown. So here we have nuclear radium decaying to radon, polonium, and actinium. If we have a look at the first decay, the atomic number is down by 2, which means that alpha decay must have taken place. We can also see that the mass number has reduced by a factor of 4, giving further indication of this. At B, we see that the atomic number again is down by 2, and the mass number is down by 4, showing alpha decay. At C, we see no change to the mass number. However, the atomic number has increased by 1, showing that this is beta decay. Example 2. We don't need to learn all the information from the periodic table. All the information will be included in any relevant questions or the information included within the periodic table, which is in your relationship sheet. Information within the periodic table will tell you the atomic number, which remember is the number of protons contained within an atom. You'll also be given the mass number, which is the number of protons and the number of neutrons. You'll be given the element symbols and their. In example 2, we want to identify the missing isotope. Remember, an isotope is an atom which has a different number of neutrons in each stage of the decay series zone. So first of all, we show alpha decay. Remember, alpha decay means we're going to reduce our mass number by 4 and our atomic number by 2. So our new mass number becomes 242 take away 4. The atomic number becomes 94 take away 2, which is 92. And from the periodic table of elements, we can find that this element is uranium. The isotope is uranium-238, 92. 238 we get from the mass number, and 92 is the atomic number. In part B, the mass number is unchanged, therefore remains at 238, but the new atomic number is +1 because we have beta decay. Thus the atomic number becomes 93. From the periodic table, we can tell that this is neptunium. In the same way, it can be found that we have nuclear decays occurring at each stage. In both alpha and beta decay, there may be gamma radiation given off as well, although we cannot include this from this study because we don't know. Nuclear fission. In fission, a large nucleus splits into two nuclei of smaller mass with the release of several neutrons and energy, as can be shown in this diagram. You need to be able to describe nuclear fission in terms of the large nucleus being split up and the fragments of neutrons and energy being released. We see in this diagram we have a neutron which is encouraging the large nucleus to split up, and that is stimulated fission as opposed to spontaneous fission, which can occur. We use stimulated fission in order to control the amount of energy produced within nuclear reactions. So fission can occur randomly, and we tend to find that larger, heavier elements with a large number of neutrons, for example uranium, will split up randomly. We call this spontaneous. Most often we have elements which will decay, and we say they have a fixed half-life. However, we can stimulate them to decay by using a neutron, causing it to undergo fission. Literally, the neutron is fired at the nucleus of the atom, causing it to split. When we measure the products of the nuclear reaction, we see that the mass of the nucleus before the fission is bigger than the mass of all the components after the collision. It's that difference in mass which is then converted into energy. Key points are as follows. E is equal to mc squared. The lost mass from the previous example is converted into energy according to Einstein's famous equation, E is equal to mc squared, where E is the energy measured in joules, m is the mass in kilograms, and c is the velocity of light, 3 times 10 to the to 8 meters per second. Please note that only the c within this equation is squared. C squared is 9 times 10 to the 16. Within the examples that you're given, you'll be given a data table which has all of the masses of the different elements, and you have to calculate the energy released from the reaction. So we have uranium, which is decaying to form beryllium, zirconium, and a neutron. We would calculate the mass after the nuclear reaction, compare this to the mass before the nuclear reaction, and then use the difference in mass within the equation E equals mc squared in order to determine the energy released. So in this example, we're asked to find the energy given out by this reaction, where we have uranium, which is stimulated with a neutron, producing beryllium, zirconium, and 4 neutrons. The first step is to find the mass before and after. So we talk about the left-hand side and the right-hand side of the equation. The mass of the left-hand side is the mass of the uranium plus the mass of the neutron, equals 3.918 times 10 to the negative 25 kilograms. A word of caution here, do not round your answers. The only rounding that should occur is when we have the final calculation of energy at the end. The mass of the right-hand side takes into account the mass of the beryllium, the zirconium, but also 4 neutrons. So you must remember to multiply the mass of the neutrons in this example by 4. It's useful to use brackets at this stage. This gives us a value of 3.915 times 10 to the negative 25. So we see the importance of not rounding here, because the difference between 3.918 and 3.915 is very small. And had we rounded at an earlier stage, we wouldn't notice the difference at all. The difference in mass is found to be 0.003 times 10 to the negative 25 kilograms. We then apply this to the equation E is equal to mc squared to give us a final value of the energy released as 2.7 times 10 to the negative 11 joules. This doesn't seem like a very large amount, but remember there are many of these reactions occurring, and all of that energy adds up. Within nuclear fusion, we have 2 smaller nuclei joining together. So we can state that nuclear fusion is when 2 light nuclei combine to form a nucleus of a larger mass number and a neutron. Like in fission, there is a decrease in mass after the fusion, and this loss in mass produces energy, E equals mc squared. However, the energy released is produced as kinetic energy of the fusion products. So the particle which is produced after the fusion reaction is given kinetic energy and moves off at velocity. Nuclear fusion normally only occurs at very high temperatures, and this explains why the energy released by the Sun and other stars is produced by nuclear fusion. Key points here is the process of fusion and how energy is released. Please note this diagram. So we see deuterium and tritium, which are two isotopes of hydrogen, combining together in order to form helium, which has a higher value of mass number. It's got a larger nucleus, a neutron, and energy. Recognizing fission and fusion. Remember, in fission reactions, the large nucleus is at the start of the reaction. In fusion, it's at the end. In stimulated fission reactions, the reactants on the left-hand side will contain a neutron. For example, the example we showed before, where we had the uranium being stimulated by the neutron. When we have a fusion reaction, the neutron will appear after the reaction. In both cases, we look at the mass difference between the left-hand side and the right-hand side in order to tell us what the energy released is going to be. So we need to apply that mass to E equals mc squared. Now let's have a look at some examples. Old Hire 2000 paper question 18. The statement below represents a nuclear reaction. This is very similar to the one we saw previously. You have to identify, is this an example of nuclear fusion, alpha particle emission, beta particle emission, spontaneous nuclear fission, or induced nuclear fission? Now we can see within this question that we have a large nucleus at the start and a neutron being introduced and two smaller nuclei. So first of all, because we have smaller nuclei produced from a large nuclei, we can say that this is fission. So A is definitely incorrect. We also have a neutron which is being introduced to the larger nucleus, suggesting that we have induced nuclear fission. So D is definitely incorrect as well. We can't see any alpha particles or beta particles being produced during the reaction. So this is induced nuclear fission, E. Now there are coolant containment issues regarded within nuclear fusion reactors. As we're aware, nuclear fusion reactions generally occur under very, very, very high temperatures. So there's a number of safety issues and concerns surrounding nuclear fusion reactors that are up for debate. Mainly, we have coolant issues. As a nuclear fusion creates incredibly high and potentially dangerous temperatures and requires those temperatures to start in the first place, coolants are required to remove the excess energy. We then need to contain that. After the nuclear fuel has been used, it can also remain dangerously radioactive for a number of years. This has to be kept in thick concrete, lead-lined containers and hidden away from the general public. Where it's stored, that land can't be used for anything else. Let's look at some past papers from the Old Hire. 2001 question 20. Under certain conditions, a nucleus of nitrogen absorbs an alpha particle to form the nucleus of another element and releases a single particle. Which of the following statements correctly describes this process? So we're looking for nitrogen absorbing an alpha particle. An alpha particle has a mass number of 4 and an atomic number of 2. So straight away we can say A is incorrect because we have helium with 3 and 2. C is incorrect because we have helium with 3 and 2. So we're left with B, D, and E. We're told that it absorbs an alpha particle to form the nucleus of another element and releases a single particle. So D must be incorrect because we're releasing 2 particles, 2 electrons. That leaves us with B and with E. Well, B is also incorrect because we're told a nucleus of nitrogen absorbs an alpha particle. Here we have nitrogen and alpha being absorbed. That bit's correct. But then we're told that it forms another element. We have the same element here. We still have nitrogen. Therefore, this is incorrect, leaving us with E. 2003 question 20. Which of the following statements describes nuclear fission? Well, nuclear fission is a nucleus of a large mass number splitting into 2 nuclei, releasing several neutrons. So that must be statement A. 2008, question 20. So the nuclear decay is shown. Which row in the table gives the correct values of X, Y, and Z? Well, first of all, we see when we've got this nuclear decay that the mass number is not going to change because the mass number of an electron, this is beta decay, is 0 here. Therefore, the value of Y must be the same as the value for the left-hand side, which is 214. So straight away, we can get rid of C and we can get rid of E. If we have a look at the bottom line, Z, that's the atomic number for an electron. We should be aware, we should know that's -1. So that gets rid of A and that gets rid of B. Let's just check for the value of X. -1 added on to 83 gives us a value of 82. So the correct answer is D. 2010, question 18. We're given the total mass of the particles before the reaction, the total mass of the particles after the reaction, and we need to calculate the energy released. We're simply working out the difference between the two masses and then applying the equation E is equal to mc squared. If you do that, you find the value to be D. Other past paper questions from the IR that you can do are as follows. Having a look now at past paper questions from the revised and CFE higher, which of the following statements describes spontaneous nuclear fission reaction? Remember, on a spontaneous nuclear fission reaction, we don't have a neutron on the left-hand side. So A is totally incorrect. Have a look at the other values. In E, we've got a large nucleus, but it's not splitting into smaller nuclei, so that is incorrect. In C, we have two smaller nuclei producing a large nuclei, so that's incorrect. In B, we're producing two helium atoms, helium nuclei, from a larger and a smaller, so that's incorrect because that's more like fusion, so the answer must be D. 2012, here a statement represents a nuclear reaction. We're given the mass on the left-hand side, the mass on the right-hand side. Again, we work out the difference in the masses and apply the equation E is equal to mc squared, giving us a value of B, 2.79 times 10 to the -12 joules. In the 2013 paper, we're looking at a transition diagram. Now, the transition diagram shows the radioactive decay that's occurring. So we have X1 to start, then goes to X2, then goes to X3, X4, and X5. We need to look at the difference in the mass number and the atomic number at each of the transitions to tell us what particle has decayed. So statement number 1 says nuclides X2 and X3 contain the same number of protons. Well, we look at X2 to X3 and we can see that we have the mass number being exactly the same, which is true. However, the atomic number has changed. It's gone from 90 to 91. Therefore, the number of protons cannot be the same. Statement 1 is incorrect. Statement 2, nuclide X1 decays into nuclide X2 by emitting an alpha particle. Well, we have X1 here, starting with an atomic number of 92, and then goes to an atomic number of 90. So atomic number has gone down by 2. The mass starts at 238, and then goes to 234. So the mass number has gone down by 4. So that's definitely alpha decay, so that's correct. Nuclide X3 decays into nuclide X4 by emitting a beta particle. Let's have a look. We go from an atomic number of 91 to an atomic number of 92. So we've added 1 onto the atomic number, but remained at the same mass. So again, that is definitely true. So statement 2 and statement 3 only are correct. So that's D. 2014 paper, an isotope of uranium decays into an isotope of protactinium in 2 stages as shown. We have the uranium decaying first of all in 1 stage for the thorium, and then stage 2 to make the protactinium. Which row in the table identifies the radiations which must be emitted at each stage? Again, we're looking at the mass numbers and the atomic numbers. The mass number has gone down by 4. The atomic number has gone down by 2. So that must be alpha. So that means B, C, and D are all incorrect. Stage 2, we see the mass number has stayed the same, but the atomic number has gone up by +1, which means that must be beta. So that is E. So in question 9 in the first CFE specimen paper, we have a fusion reaction and we're given the masses of the particles involved within the reaction, and we need to calculate the energy released in the reaction. So here's the key information from the question. We're asked to determine the energy released during the reaction. So the first thing we need to do is have a look at the difference in mass. So we look at left-hand side, right-hand side. So for the left-hand side, mass is equal to 4 times the mass of a hydrogen atom, which is 1.673 times 10 to the negative 27. Now I'm just leaving it like this right now. I'm not doing the calculation yet, just in case I make a mistake. On the right-hand side, the mass is equal to 6.46 times 10 to the negative 27. Both of these are kilograms. That's because the mass of an electron is negligible. It's not zero, but it's negligible. We then work out the difference in mass. So here's why I kept everything within the brackets. Because me writing 4 times 1.673 times 10 to the negative 27 means I'm definitely substituting in the correct values. And if I definitely substitute in the correct values, I get the marks. Do that calculation, you end up with a difference in mass of 4.6 times 10 to the negative 29 kilograms. You're then going to apply the equation. E is equal to mc squared, which is equal to 4.6 times 10 to the negative 29 multiplied by 3 times 10 to the 8 squared. Remember, we're only squaring the c term. We're not squaring both the m and the c. Put that together, you end up with 4.14 times 10 to the negative 12 joules. We would also accept 4.1 times 10 to the negative 12 joules. That's absolutely fine. Okay, so in part 2, we're asked to calculate the energy released when 0.2 kilograms of hydrogen is converted to helium by the reaction. We need to remind ourselves of some key information within the question, that is the mass of a hydrogen atom and also the reaction itself. So we've already calculated how much energy is released during one nuclear reaction. What we need to do is we need to find out how many hydrogen atoms we have to deal with, remembering that we need 4 hydrogen atoms in order for a reaction to take place. So let's work out how many hydrogen atoms we have within 0.2 kilograms. So the number of hydrogen atoms is equal to 0.2 kilograms divided by the mass of one single atom, which is 1.673 times 10 to the negative 27. And that works out to be 1.195 times 10 to the 26 atoms. Now to find out about the number of reactions, we need to take the number of atoms and divide it by 4, because we know every individual reaction needs 4 hydrogen atoms. So the number of reactions is equal to 1.195 times 10 to the 26 atoms divided by 4, which is equal to 0.2989 times 10 to the 26. Notice no rounding here. Not yet. So we know we get this number of reactions. We also know the energy released during each reaction. So that means energy released is equal to the number of reactions multiplied by the energy per reaction. So we'd need to look back at our previous answer, but this works out to be 0.2989 times 10 to the 26 multiplied by 4.14 times 10 to the negative 12, or whatever value you had, because you may have calculated a different value. So you get the marks as long as you're consistent. And that is equal to 1.2 times 10 to the 14 joules. So we can see that although each individual reaction produces a very small amount of energy, within a very small mass of uranium or hydrogen or whatever you're using for the nuclear reaction, a very small quantity of that can produce a very, very large number of reactions, millions and billions of reactions, and therefore we produce a large amount of energy. In part 3, we're told that fusion reactors are being developed that use this type of reaction as energy source, and they are. Explain why this type of fusion reaction is hard to sustain in these reactors. Well, there's lots of different reasons for this. Mainly, though, we're looking at large amounts of energy is released, which results in very high temperatures. We could then say that in order to contain this, we need to use strong magnetic fields. So strong magnetic fields are required to contain the reaction. In this question, the diagram shows part of an experimental fusion reactor. The following statement represents a reaction that takes place inside of the reactor. So we see two isotopes of hydrogen combining to form helium and a neutron. The masses of the particles involved are given in the table, and just a reminder of the reaction there. First of all, we're asked to explain why energy is released in this reaction. Well, energy is released because we have that change in mass. For the SQA, it's enough for us just to say that mass is converted into energy. We're then asked to calculate the energy released in the reaction. The information that we need for this is contained within the data that was on the previous slide. As with all nuclear reactions, we need to calculate the mass before the reaction and the mass after the reaction. So the mass before is equal to the mass of the two isotopes of hydrogen. So that's 3.3436 times 10 to the negative 27 plus 5.0083 times 10 to the negative 27, which is equal to 8.3519
times 10 to the negative 27. That's kilograms, though we don't specifically need the units just now because this is just part of the working. The mass after is equal to the mass of the helium produced plus the neutron. So that's 6.6465 times 10 to the negative 27 plus 1.6749 times 10 to the negative 27, which is equal to 8.3214 times 10 to the negative 27, again, kilograms. Notice we don't do any rounding at this point whatsoever because rounding is going to affect our answer. We then work out our change in mass from after and before, and that's equal to 3.0500 times 10 to the negative 29 kilograms. So that's our change in mass. Now what we need to do is to calculate how much energy is released. We use the equation E is equal to mc squared, which is equal to 3.0500 times 10 to the negative 29 multiplied by the speed of light squared, 3 times 10 to the 8 squared, which is equal to 2.75 times 10 to the negative 12 joules. So the only time we do rounding is right at the very end. This avoids us making mistakes because we're dealing with very, very small numbers here. There's lots of numbers on this page. So the way to keep yourself accurate is to lay it out properly. Mass before, mass after, change in mass, and then E is equal to mc squared. The next part of the question saying magnetic fields are used to contain the plasma inside the fusion reactor. Explain why it is necessary to use a magnetic field to contain the plasma. Well, there's a number of different reasons. The main one would be that the plasma is going to cool down if it came too close to the sides. And if the plasma came too cool, then that means that the reaction is not going to continue. So we can say that the reaction requires a very high temperature if not contained, a number of different reasons could happen. Either we would accept that the plasma will cool down, or we could say that the plasma could melt the sides of the reactor. That's nuclear meltdown. Or we could say the high temperatures could damage the container. Okay, so any of those would be accepted, but specifically we need to mention that reaction requires very high temperatures, and these temperatures need to be contained. The last part of the question, we're going back to electric fields and magnetic fields. Plasma consists of charged particles. A positively charged particle enters a region of the magnetic field as shown. Determine the direction of the force exerted by the magnetic field on the positively charged particle. So we have positively charged particles, so we're using the left-hand rule here. We can see from the crosses that the field is going into the page. The positively charged particle is moving to the right. So as you would normally have the left-hand rule, you don't need to do any movement orientation. you should see that the force on that charged particle, your thumb should be pointing up. So we say up the page. Obviously, just the word up or upwards would be accepted there. You would also be allowed to just draw an arrow to show the upwards direction.